Welcome to today's session on LeetCode problem number 312, burst balloons. In this problem, we'll explore how to maximize the coins collected by bursting balloons in a strategic order. We'll break down the problem, discuss possible approaches, and work towards the most optimal solution. Let's get started. In this problem, you are tasked with bursting a sequence of balloons to maximize the number of coins you can collect. Each balloon has a value, and when you burst a specific balloon, the coins you gain are calculated as the product of its value and the values of the balloons immediately to its left and right. If there's no balloon on the left or right, we treat it as if there's a virtual balloon with a value of 1. Your goal is to determine the maximum coins you can collect by carefully choosing the order in which to burst the balloons. The input is a list of integers representing the values of the balloons, and the output is a single integer indicating the maximum coins you can earn. For example, if the input is 3, 1, 5, 8, the maximum coins you can collect is 167. Let's explore some examples to understand this further. Consider the input nums equals 3, 1, 5, 8. To handle edge cases, we add two virtual balloons with a value of 1 at both ends, resulting in nums equals 1, 3, 1, 5, 8, 1. The optimal order to burst the balloons is as follows. First, burst the balloon at index 1 with a value of 3, which gives 3 coins. Then, burst the balloon at index 3 with a value of 5, earning 40 coins. Next, burst the balloon at index 2 with a value of 1, which adds 8 coins. After that, burst the balloon at index 1 with a value of 8, earning 8 coins. Finally, burst the balloon at index 1 with a value of 1, which adds 1 coin. Adding these together gives a total of 167 coins. This demonstrates how choosing the right order can significantly affect the result. Now let's look at a simpler example with nums equals 1, 5. Adding virtual balloons at both ends gives nums equals 1, 1, 5, 1. The optimal order here is to first burst the balloon at index 1 with a value of 1, which earns 5 coins. Then, burst the balloon at index 1 with a value of 5, which adds another 5 coins. The total coins collected in this case is 10. This example highlights how even with fewer balloons, the order of bursting matters to maximize the coins collected. In the case where there's only one balloon, such as nums equals 7, the problem is straightforward. Adding virtual balloons results in nums equals 1, 7, 1. Here, there's only one option, burst the balloon at index 1 with a value of 7. This earns you 7 coins, and the total coins collected is 7. This example illustrates a base case where the solution is immediate due to the lack of choice in the bursting order. Finally, let's consider some edge cases. If the input contains only zeros, such as nums equals 0 or 0, 0, the result is 0 since there are no coins to collect. For a single balloon, like nums equals x, the result is simply the value of that balloon x. When all balloons have the same value, such as nums equals k, 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 the order of bursting will determine the intermediate steps, but the maximum coins collected will always be the same. For the largest input size, or len, nums, equals 300 and all values are 100, the solution must handle the problem efficiently while respecting the constraints. These cases emphasize the importance of an optimized approach to solve the problem within the given limits. To solve the burst balloons problem, the most straightforward approach to consider is a brute force method. The intuition here is to simulate the process of bursting balloons one by one, calculating the coins obtained for each choice, and then recursively solving the subproblems for the remaining balloons. Specifically, for each balloon I, the coins gained can be computed as the product of its value and the values of its immediate neighbors, nums, left, asterisk nums, I, asterisk nums, right. After bursting I, we solve the subproblems for the intervals to the left and right of I recursively. Finally, we return the maximum coins obtained across all possible orders of bursting the balloons. However, this approach involves recursively exploring every possible sequence of bursts, leading to an exponential time complexity. While it's simple to understand, it quickly becomes infeasible for larger inputs due to the sheer number of computations involved. To overcome the inefficiency of the brute force method, we can optimize the solution using dynamic programming. The key insight is to recognize that bursting a balloon depends only on its immediate neighbors, which remain fixed until the balloon is burst. This allows us to break the problem into overlapping subproblems and store their solutions to avoid redundant computation. To simplify the calculations, we add two virtual balloons with a value of 1 at the boundaries. Then, we define a DP table DP, I, J, where each entry represents the maximum coins obtainable from bursting all balloons in the range, I, J. By iterating over all subranges, I, J, in increasing order of length, we can compute the maximum coins for each subrange. For a given subrange, we consider every balloon K within I, J, as the last balloon to burst. The coins gained by bursting K are calculated as nums, I1, nums, K, nums, J plus 1, plus the coins obtained from solving the subproblems for the intervals to the left and right of K. We update DP, I, J, with the maximum coins over all choices of K. By the end of this process, the result is stored in DP, 1 where n is the number of balloons after adding the virtual boundaries. This dynamic programming approach reduces the time complexity to O, n cubed, and the space complexity to O, n squared, making it much more efficient than brute force for larger inputs. The dynamic programming approach is the most suitable strategy for this problem because it efficiently handles overlapping subproblems and avoids the exponential complexity of brute force. By solving smaller subproblems first and iteratively building up to the larger ones, it ensures that all dependencies are resolved beforehand. The key insights, such as treating the problem as range-based DP and adding virtual boundary balloons, simplify the implementation and make the solution scalable for larger inputs. When comparing the strategies, the brute force approach is easy to understand and directly aligns with the problem statement. However, its exponential complexity makes it impractical for larger inputs. The dynamic programming method, in contrast, reduces the complexity to O, n cubed, allowing it to handle up to n equals 500 balloons efficiently. While it does require O, n squared, space for the DP table, this is a reasonable trade-off for the significant performance improvement. Another alternative is a memoized recursive solution, which combines the simplicity of recursion with the optimization of DP. However, it is less intuitive than the iterative DP approach. Overall, dynamic programming provides the best balance between simplicity, efficiency, and scalability, making it the optimal choice for solving this problem. To solve the burst balloons problem, we want to maximize the coins collected by carefully choosing the order in which balloons are burst. The key observation here is that bursting a balloon at index I contributes coins based on its adjacent balloons, specifically nums, left, nums, I, nums, right. If there is no adjacent balloon on either side, we treat it as having a value of 1. This ensures that every burst operation is localized to the current balloon and its immediate neighbors. Now, a brute force approach to solve this problem involves defining it recursively. For each balloon, we calculate the coins earned by bursting it first among the remaining balloons, then recursively solve the subproblems for the balloons on its left and right. To determine the optimal solution, we iterate over all possibilities within each subproblem. If we encounter a scenario where no balloons remain, the base case simply returns 0 coins. To avoid redundant calculations, we implement memoization, which stores the results of previously solved subproblems, significantly improving efficiency. This approach, while straightforward, can still be computationally expensive due to the large number of recursive calls and overlapping subproblems. A more efficient solution leverages dynamic programming to optimize the brute force approach. The first step is to extend the nums array by adding 1 at both ends, so the array becomes 1, nums, 0, nums, and 1, 1. This simplifies boundary conditions because we can always assume there are adjacent balloons with a value of 1. Next, we define a 2D DP table DP, I, J, where DP, I, J, represents the maximum coins obtainable by bursting all the balloons in the range I to J, excluding the boundaries at I and J. We then iterate over subarray lengths, starting from smaller ranges and gradually increasing the length. For each subarray, we evaluate all possible balloons to burst last. The coins collected in this scenario are the product of the current balloon's value and its adjacent values, which are nums, left 1, nums, K, nums, right plus 1. Additionally, we include the maximum coins obtained from the left and right subarrays, stored in DP, left, K1, and DP, K plus 1, right. Finally, DP, left, right, is updated to the maximum value across all possible choices. The result of the problem is found in dp1 n, where n is the size of the original array. This problem has several key insights that make it well suited for dynamic programming. First, it exhibits optimal substructure, meaning the solution to the overall problem can be constructed from solutions to its smaller subproblems. The coins obtained by bursting a particular balloon depend only on the balloons immediately to its left and right, which simplifies the problem's decomposition. Second, extending the array with 1 at both ends eliminates edge cases, ensuring that there's always a left and right balloon to consider. Third, memoization or dynamic programming avoids redundant calculations by storing the results of overlapping subproblems. This drastically reduces the time complexity compared to a purely recursive approach. Another critical insight is that the choice of the last balloon to burst in a subarray has a significant impact on the result. Evaluating all options for this choice ensures that we find the optimal solution. To implement this efficiently, we use a 2D dynamic programming table to store maximum coin values for each subarray, and we leverage the extended array to handle boundary conditions seamlessly. The time complexity of this dynamic programming solution is O(n cubed). This is because we have O(n squared) subarrays to consider, and for each subarray, we iterate over O(n) possible last balloons to burst. The space complexity is O(n squared) as well, due to the dp table that stores the maximum coins for each subarray. Several edge cases must also be addressed. If the input array is empty, the result should be 0 since no balloons are available to burst. For a single balloon, the result is simply its value, as it is the only option. When all balloons have the same value, the algorithm must ensure it handles uniform values correctly without any unintended behavior. Finally, for large inputs, the algorithm must be efficient and scalable, leveraging the dp table to manage the computational complexity effectively. These considerations ensure the solution is robust and performs well across a wide range of scenarios. This solution uses dynamic programming to efficiently solve the burst balloons problem. First, we pad the input array nums with 1s at both ends to simplify boundary conditions. This ensures every balloon burst is always surrounded by valid numbers. We then define a 2D dp table, dp, where dp, left, right, represents the maximum coins obtainable by bursting all balloons in the subarray nums, left to right plus 1, exclusive of boundaries. The algorithm iterates over subarray lengths from 2 to n1, inclusive. For each length, we calculate the maximum coins for every possible subarray, left to right plus 1, within nums. For a fixed subarray, we try bursting every balloon I in the range, left, right, as the last balloon. The coins gained are nums, left, asterisk nums, I, asterisk nums, right, plus the coins from recursively solving the subproblems dp, left, I, and dp, I, right. We take the maximum over all choices of I. Finally, dp, 0, and 1, contains the result, representing the maximum coins obtainable by bursting all balloons in the original array. This approach has a time complexity of O(n cubed), where n is the length of nums after padding, making it efficient for the given constraints. Here, we begin by importing the necessary libraries and defining our solution class. The main method, maxCoins, takes an array of integers called nums, where each integer represents the value of a balloon. To simplify the problem, we add 2 boundary balloons with a value of 1 at the beginning and end of the array, creating a new array called extended nums. This allows us to handle edge cases more easily, such as when the first or last balloon is burst. Next, we initialize a 2-dimensional dp table, where dp, left, right, will store the maximum coins obtainable for the subarray from extended nums, left, to extended nums, right. To calculate this efficiently, we use a bottom-up dynamic programming approach. We iterate over all possible subarray lengths, starting from 2 since we need at least 2 boundaries to calculate the coins. For each subarray, defined by its left and right boundaries, we iterate through all potential balloons that could be burst last within that subarray. This is represented by the variable I. The value at dp, left, right, is updated to the maximum of its current value and the coins obtained by bursting balloon I plus the coins obtainable from the 2 smaller subproblems on either side of I, which are stored in dp, left, I, and dp, I, right. This way, we build the solution incrementally for all possible subarrays. Finally, after filling up the DP table, the maximum coins obtainable for the entire range of balloons, including the boundary balloons, will be stored in DP 0 n plus 1. This is because DP 0 n plus 1 represents the subarray that spans from the first boundary balloon to the last boundary balloon, encompassing all the balloons in the original input array. We return this value as the result. This approach ensures that we efficiently calculate the maximum coins by exploring all possible ways to burst the balloons while avoiding redundant calculations, thanks to the dynamic programming table. The time complexity of this solution is O n cubed, as we have 3 nested loops, one for the subarray length, one for the left boundary, and one for the potential last balloon to burst. Despite this, it's an optimal solution for the constraints of this problem, leveraging the idea of divide and conquer with dynamic programming. To approach this problem, we start by modifying the input array nums to include boundary balloons with a value of 1 at both ends. This ensures that we can calculate coins for any burst operation uniformly, even at the edges of the array. After adding the boundaries, the new array becomes 1, 3, 1, 5, 8, 1. The length of this updated array is n equals 6. Next, we initialize a dynamic programming table, or DP table, which is a 2D array of size 6x6 filled with zeros. This table will help us store the maximum coins obtainable for every possible subarray of nums. Each cell DP, left, right, will represent the maximum coins we can collect by bursting all the balloons between indices left and right, exclusive of the boundaries. With this setup, we're ready to begin the computation process. Now we compute the maximum coins using a bottom-up approach, iterating over all possible subarray lengths from 2 to n1. For subarrays of length 2, there is only one balloon to burst in each interval. For the subarray, left equals 0, right equals 2, the only balloon is at index 1, so the coins collected are nums, 0, asterisk nums, 1, asterisk nums, 2, is equal to 1 times 3 times 1 equals 3. We update DP, 0, 2, to 3. Similarly, for left equals 1, right equals 3, the only balloon is at index 2, giving coins nums, 1, asterisk nums, 2, asterisk nums, 3, is equal to 3 times 1 times 5 equals 15, so DP, 1, 3, is updated to 15. For left equals 2, right equals 4, bursting the balloon at index 3 yields coins nums, 2, asterisk nums, 3, asterisk nums, 4, is equal to 1 times 5 times 8 equals 40, so DP, 2, 4, becomes 40. Finally, for left equals 3, right equals 5, bursting the balloon at index 4 gives nums, 3, asterisk nums, for asterisk nums, 5, is equal to 5 times 8 times 1 equals 40, and DP, 3, 5, is updated to 40. These calculations establish the base cases for our DP table. For subarrays of length 3, we consider multiple options for the last balloon to burst. For the subarray, left equals 0, right equals 3, we can choose either balloon I equals 1 or I equals 2 as the last balloon. If we burst balloon I equals 1, the coins are calculated as nums, 0, asterisk nums, 1, asterisk nums, 3, plus DP, 0, 1, plus DP, 1, 3, is equal to 1 times 3 times 5 plus 0 plus 15 equals 30. Alternatively, if we burst balloon I equals 2, the coins are nums, 0, asterisk nums, 2, asterisk nums, 3, plus DP, 0, 2, plus DP, 2, 3, is equal to 1 times 5 plus 3 plus 0 equals 8. The maximum of these two options is 30, so we update DP, 0, 3, to 30. Similar calculations are performed for other subarrays of length 3. Once all computations are complete, the final result for the entire array is stored in DP, 0, and 1, which is DP, 0, 5. For this example, DP, 0, 5, equals 167, representing the maximum coins we can collect by bursting all balloons in the array. For the second example where nums equals 1, 5, we follow the same process. First, we add boundary balloons to get 1, 1, 5, 1. Then, we initialize a 4x4 DP table filled with zeros. For subarrays of length 2, we calculate the maximum coins for each interval. For left equals 0, right equals 2, the only balloon to burst is at I equals 1, producing coins nums, 0, asterisk nums, 1, asterisk nums, 2, is equal to 1 times 5 equals 5. We update DP, 0, 2, to 5. Similar calculations are done for other intervals. After completing these computations, the maximum coins for the entire array are stored in dp 0, 3, which equals 10. This is the optimal result for this example, obtained by bursting the balloons in the best possible order. To analyze the time complexity of this solution, we start by looking at the loops in the code. The outermost loop iterates over possible subarray lengths, starting from 2 up to n1. This means there are approximately n iterations for this loop. Next, for each subarray length, the second loop iterates over all valid starting indices, which depends on the current length. For instance, when the length is 2, the loop iterates n 2 times, for length 3, it iterates n 3 times, and so on, until we reach a single iteration for the largest subarray length. Adding these up for all lengths gives a total of roughly n squared iterations for the second loop. Lastly, the innermost loop processes all possible balloons to burst between the current left and right indices. Its iterations depend on the gap between these indices, which corresponds to the current subarray length. Aggregating the work done by this innermost loop across all subarrays results in a total of about n cubed iterations. Combining these loops, the overall time complexity becomes O, n cubed. When we combine the contributions of all the loops, we determine that the algorithm has a total time complexity of O, n cubed. Now let's turn to the space complexity. The primary contributor to space usage is the dynamic programming table, which is a 2D array of size n by n. Since n includes the original array plus 2 boundary balloons, the table requires O, n squared, memory. Aside from this, the algorithm uses a constant amount of additional space for variables like left, right, and I in the loops. This constant space contributes O, 1, and does not impact the overall asymptotic complexity. Therefore, the total space complexity is dominated by the dp table, resulting in O, n squared. To better understand the improvements of this approach, let's compare it with a brute force solution. A brute force method would involve recursively trying all possible orders in which the balloons could be burst. With n balloons, the number of permutations to consider is n factorial, or O, n. For each permutation, the cost of bursting balloons depends on the number of remaining balloons, making this approach computationally infeasible for even moderate values of n. By contrast, the dynamic programming solution uses overlapping subproblems and avoids redundant computations, reducing the time complexity from O, n, to O, n cubed. This is a significant optimization, making the approach practical for real-world input sizes. Additionally, because the solution processes all subarrays in burst orders in a structured manner, the best, average, and worst-case scenarios all consistently exhibit the same O, n cubed, time complexity. Now, let's confirm the time complexity mathematically. Each of the 3 nested loops contributes O, n, iterations, 1 for the outer loop over lengths, 1 for the second loop over left indices, and 1 for the innermost loop iterating over potential balloons to burst. Multiplying these together gives us O, n, times O, n, times O, n, which equals O, n cubed. This matches our earlier analysis of the algorithm's behavior. For space complexity, the dynamic programming table, as a 2D array, requires n by n storage, leading to O, n squared, memory usage. The auxiliary space, being constant, does not affect the overall asymptotic complexity. In summary, the dynamic programming approach reduces the time complexity from the brute force O, n, to O, n cubed, while maintaining an efficient space usage of O, n squared. This remarkable improvement makes the algorithm both scalable and efficient. When solving the burst balloons problem, there are several common pitfalls to watch out for. One major issue is neglecting edge cases. For example, what happens if the input list is empty, has only one element, or contains duplicate values? These scenarios might seem rare, but failing to handle them can lead to runtime errors or incorrect outputs. Another frequent mistake is using a recursive solution without memoization. While recursion can be intuitive, it often leads to exponential time complexity if you don't store intermediate results. This happens because you end up solving the same overlapping subproblems repeatedly, which significantly increases runtime. Similarly, incorrect base cases in recursion can cause infinite loops or wrong results, so it's vital to carefully define the stopping conditions for your smallest subproblems. Additionally, some solutions mistakenly assume the input is already sorted, which can produce incorrect results if sorting isn't explicitly handled. Lastly, boundary or index errors are quite common in dynamic programming and recursion problems. These off-by-one mistakes, especially when working with ranges, can be subtle but impactful. Double-check how you're handling indices and boundaries to ensure correctness. Now, let's focus on some valuable insights for tackling this problem in interviews. Recognizing patterns quickly is a key skill. Many optimization problems involving subarrays, subsequences, or maximizing values can often be approached with dynamic programming. Identifying this early can save you precious time. Once you know DP is the right approach, it's important to clearly define your state, transitions, and base cases before diving into the code. For instance, if the problem involves intervals or partitions, think carefully about how to represent the state. A common choice is something like DP, I, where I, represents a specific subproblem. Also, consider the trade-offs between brute force and optimized solutions. While brute force can help clarify the problem, it's not efficient, but it often reveals overlapping subproblems, which can lead you to a DP or divide-and-conquer solution. Look out for opportunities to optimize further, such as reducing space complexity. For example, if your DP solution only relies on the last state, you can use rolling arrays instead of storing the entire table. Finally, be thorough when explaining your approach to edge cases. Interviewers often test your ability to think critically about edge scenarios, so proactively addressing them can leave a strong impression. To broaden your understanding, it's helpful to explore related problems and alternative approaches. For instance, burst balloons itself is a classic example of interval dynamic programming, but you might also want to look at LeetCode 516, which focuses on finding the longest palindromic subsequence, another interval DP problem. LeetCode 887, the super egg drop problem, is another fascinating optimization challenge using DP, albeit with a different state space. And then there's LeetCode 1143, which involves finding the longest common subsequence, a classic DP problem when comparing sequences. Now, while the most common solution for burst balloons is dynamic programming, alternative approaches can sometimes be useful. Divide and conquer, for example, can work when subproblems are independent, but without memoization, this risks redundant calculations. You might also consider greedy algorithms for simpler variations of the problem, though they generally fall short for interval-based problems where future decisions depend on earlier choices. Lastly, if recursion with memoization feels complicated, iterative DP can be a more straightforward option. It's easier to debug and avoid stack overflow issues in languages with limited recursion depth. Great job following through. In summary, we tackled the burst balloons problem by examining brute force and dynamic programming approaches. The key takeaway is the power of dynamic programming in solving problems with overlapping subproblems. Thanks for watching, and don't forget to like and subscribe for more exciting coding challenges and solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!